let's get started. It's getting smaller and smaller. All right, so class feedback, about 30% they said had filled out the IACS class feedback, which is specifically about undergrad versus grad and PhD students. It's LinkedIn Piazza post 529. If you haven't filled that out, please just take a little bit. I don't know how long it is. I didn't check. Final projects, do review the projects page on the class website. Especially look at, there are a few, I mean, just due to bit rot, it links previous years. Some of those are no longer valid. Some of them still are there, including like their videos and stuff like that. So go to the lists from the previous, I forget which years we have linked, 2012, 2013, or 11 and 12, something like that. Go there, find one of the ones or a few that still exist and are still, the web page and whatever is still there, and look over it. All right, it'll give you a good idea what to aim for. Just to remind you of dates, the 6th of December, your screencast, like 2 minutes, which we'll watch in class a week after. Those videos are due then. 7th and 9th, actually the day after. These two classes, we'll just watch people's projects and possibly talk a little bit about them. Attendance is still required, but we won't take it, but I'll notice if you're not here. And I know all of your names by now. As long as I have the Piazza map up, or the Canvas map up. And then on the 10th, the code and websites, everything is due. There are no late days on projects. There are no late days on projects, okay? None. They are due those days. Yes? Do we have class on the 4th? We have 2 more classes lectures after this one, which are, the 4th I think I marked down as not class. Is it marked as class on the class schedule? Yeah. It's in the reading period. I think I gave that one off. I think my plan's. Okay, so my plan and what I think, I don't know if that matches this, is there's today's lecture and then 2 more lectures, Monday and Wednesday next week after the break. And then after that, some time off, and then the 7th and 9th, watching videos. Anyway, okay. So today, I saw all the requests for various topics going forward. Today we'll do the MPI intro, and then the next 2 will be things like parallel, patterns in parallel processing and pitfalls, and wrap up. So today we'll talk about MPI. MPI is again, we're out of multi-core now, we're back to Sparkland, basically multiple processors, usually in a cluster. MPI is from the scientific community, particularly physics, atmospheric studies, people like NASA. Some of the really big machines you hear about, Blue Gene, Blue Water, all these really huge ones often have MPI. It's meant to take advantage of very large clusters efficiently. Particularly, it wants to map, it has ideas, well, there are many implementations of it. Often a vendor who's built a large cluster will provide a tuned implementation that knows about the physical structure of the machine, or the machines, how they're connected, and uses this to its advantage. So all communication is by message passing. We have separate processes running on separate machines, possibly multiple processes on a single machine. But there'll definitely be multiple machines involved. Or not definitely, but almost certainly if you're doing some large MPI project. They have independent memory spaces. There's no locking or anything like that. It's entirely by message passing. It's a library, and there are several libraries. It has a standard, it's implement such and such features, but it's not compiler supported like OpenMP, where you put in compiler directives and different things happen in your code for multiple threads. So it's just a library you call into to send messages. There are implementations in C and Fortran and Java and all kinds of things. On I'm going to talk mostly, I'm just going to reference the MPI for Pi implementation. There's another 1 or 2 implementations even for Python. They're all fairly similar. They all support the MPI at a fairly low level in terms of mapping to the C and Fortran implementation. You can use it on multi-core, and my examples will of course run there. But again, it's more meant for clusters and supercomputers. Okay. So the central idea or sort of tool in MPI are communicators. And all the processes that talk together or can talk together are organized into these communicators, basically groups of processes that can talk to one another. And there might be multiple communicators, sort of groups, subgroups, active at any time, depending on how you map your problem. And each communicator or each process in a communicator has a unique ID, a rank, it's called. That's already said. You can have multiple communicators. So you start off, you always have this COM world. You start up an MPI process, a group of processes with whatever method, and you get a bunch of processes running, and you've got this MPI COM world, which is the global everything communicator, and everything has its own unique ID, whichever processes you've run, arbitrarily assigned. You can sort of assume at the beginning, or you may not, you can't make assumptions by default at the beginning. And again, you might set up a subset for some subproblem or some particular mapping, where you get a separate communicator, and in there, they all have their own rank as well, right? So they have their global rank in the COM world. They have, if they're involved in some subset of computation, they'll have a rank there as well, right? It's just a unique ID, 0 to whatever. It'll be packed, it won't be arbitrary values, it'll be 0 to n. But you might have multiple sort of names, depending on whether you're talking about the global communicator, some subgroup communication. Basically just the group, you've got group membership and you've got some sort of ID within that group. You can get the size of communicator, you can get your rank to get, which are sort of like OpenCLs, get global size, get global ID, or local, whatever. There's no real local global separation here, but basically those same two functions to just query in your code. Who am I? How many friends do I have in this group? So here's a simple example in Python. So get the MPI, get the communicator, the global communicator, find out how many there are in the global communicator, get the per process rank, and then print some value. And to run with 4 processes, and MPI, you want to start at multiple processes, and the way you do that is you run MPI exec. If I run a cluster, this might launch things all over the place. If I just run it on my local machine, it'll do something different. So I'm saying run with 4 processes, and then run this process. It sets up the environment, it sets up all the information so they can communicate with each other, gives them their IDs, and then launches it. Yes? For Python, yes? Okay, it can all be done from Python. You have experience with this, right, for your final project. All right. So it can be done from Python. I don't know the details of MPI and Python, the most clean way to do it. Does Python have special support for? I mean, you could attach to the C library, but I assume there's something cleaner. To the low, okay. So Python, okay. So if you do this, you're probably going to be in Python because you're probably going to be doing some fairly heavy, or something like that. You're going to be doing some heavy computation. Apparently there's Python support. I haven't used it, so I'm not going to try to talk knowledgeably about it. We'll just talk about this is good enough for getting started and understanding the ideas behind MPI and how you might use it. All right, so when I do this, right, I run 3 of them. Oh, wait, that wasn't the right one. Oh, I don't think I have the right one. All right, whatever. You can predict what happens. When I run this, where's my output? When I run this, it will print out, if I run it with 4, I'll get 4 lines of printout. Each one is just going to say, my size is 4, and 0, 1, 2, 3 for the unique ranks. After the class, I'm going to put some examples in the class GitHub repository. That one will be there as well. So this is interesting just for getting started. But how then do you do message patching? This is the primary way things communicate. The usual way, the sort of basic way, is you send them with a send and receive. Sender calls send, a message, some destination rate, possibly some other flags to direct the communication. The receiver calls receive, has to be active. It's not just you get a message. Has to ask for a message from the sender. You can sometimes say just any sender, but the receiver has to actively request the message or be ready for it. Because the sender might hang until the receiver actually gets the message. Right, the sender will start sending it, and if it's a long message, it might take a while, and it may not have enough buffer space, and so it has to wait until the sender is ready to catch it, or receiver is ready to catch it and starts taking in data. If there's no receive, then the sender will definitely eventually hang. It's going to try to send more messages. It's going to back up. No one has accepted its messages. It's going to stop. All right. So here's a very simple send and receive example, which I actually just ran. So again, it sets up the com, gets the size, gets the rank, and then sets up a little bit of data right here. Just going to say, OK, I'm going to take my rank and stick it in a Python dictionary. I'll put it in a value. And then I'll send the data. And the destination is going to be my rank. Right? This is running in multiple processes. So this is separate for each one. This is sort of like CUDA. Or, well, it's like everything we're talking about. But this computation is taking place in multiple processes. Each one is going to say, OK, send to the one higher than me, but don't go over the end. And then receive from whoever's sending to me. So everything's just shifting one up and receiving from, shifting to the right and receiving from the left. And then I'll just print out the answer. Okay, and that's actually the example I just ran. Okay, so just what we saw there. When I run it with 3, I put in a little bit, instead of A, I use source rank so we can see what's going on. And the first value is the rank of whichever process received that message, and then it says what it received. So process 1 received from 0, and that value, all the values are the same. 0 received from 2, because we wrapped around with the mod operator, and 2 receives from 1. Right? So simple. All right. So the destination, they each actively say, where am I sending data to with the send, give a destination, and actively, where am I receiving data from? So it just looks like this, right? We start off with just, they're not connected. They're just a bunch of processes running in the communicator. We're basically saying, organize yourself in a line based on your rank, pass data to the right, wrap around. Clear so far? If you do use MPI for Pi, there are a couple of there are different implementations. There's the high level and low level. The capitals are the low level. It's a little strange in my mind. For those, they're much more efficient. They work directly with buffers. So here is the more complicated example where I set up a couple of buffers for data out, data in. And then when you send, you give it a buffer and a type so that it knows what it's communicating. And again, when you receive, you set the buffer and the type. But otherwise, it's exactly the same. We set up separate buffers so that we're writing from one or reading from one, writing to the other. And this gets a little hairy just because you have to be careful with the types, the buffer sizes. MPI will happily hand off a buffer pointer of an int type and say write stuff here, and it'll receive a float input and just write whatever's in there, and then you look at your data and it's totally random, right? It's when you get a mismatch pointer type or whatever. There are some checks, but it doesn't make any sort of. It's not very in-depth or not very. It's very easy to screw up the types here and then get random answers that you don't expect. So again, you use the capital versions for the low level, and then give more information and give a buffer. And then usually just NumPy arrays. So because they're doing raw communication, there's no serialization. There's still communication overhead, but it doesn't have to turn it into some sort of universal format beforehand. But and then the high-level ones, you can send just arbitrary Python objects. The other nice thing is you don't have to do any of this buffer pre-allocation. You just send a dictionary, and you get back a Python object. And below, in the library itself, it handles all of the buffering, all the buffer setup, communication, and teardown for you instead of having to do it. You pay the price for that because you allocate a bunch of memory, convert the object, communicate it, deconvert it, and then throw away the data, or throw away the message. But in general, if you're doing something high level where you need to pass dictionaries around or something like that, it's very nice. All right, so that's the basics, right? You could build everything you need pretty much from that. And some of the implementations, that's really all that's what they do. They implement these very basic communicate, point to point, simple values. But there are a bunch of things on top of that that make it a lot nicer. So especially for large simulations that map to a physical space, you have these, you can set up, Cartesian grids are just arbitrary grids, but Cartesian is a natural one to talk about, where you get nice, basically you get a nice communication topology that maps onto, you map it onto your problem. You set up a certain number of processes for each subdomain of your problem, and then create a grid that allows you to communicate between the processes spatially. So I'll just talk about Cartesian, a simple Cartesian grid. So we get the global communicator again, where everyone lives. And then we're going to say, okay, we're going to say, I want a 2x3 communication grid. We'll talk about periods and reorder in a second. And then I set up this other communicator, the Cartesian communicator, which has these dimensions and these other flags. And so what this does is, okay, I've got 6 processes running. I want to get a Cartesian grid of 2x3. And we'll just assume NumPy indexing. And so it says, do this. Organize yourself somehow in a grid, please. Nothing really has happened here except now they all have this idea of where they live in the grid, and MPI takes care of assigning them. And then you can ask, okay, well, who is next to me? You can use this, which is this shift command. And it's basically like this. I say, I take my Cartesian communicator and say, I want a shift in the first dimension of 1. So the first dimension in this case, we'll say is horizontal, and a certain distance. How far away do I shift in that dimension to find a neighbor? So when I run that command, for example, for the center one, it says your left source, it returns a left source and a right dest. It says, okay, your left source is 0, your right dest is 3. And then for this one, it says your left source is not a process, because you're at the edge. Your right source is 1. And for this one, left source is 1, right dest is not a process. It's hanging off. So, and then now I have source and dests. So if I want to actually transfer data, I can just use those values like this, right? I'll set up some data. I'll set my destination to my right dest. I'll set my source to my left source, and I just run this. And it works. And this is part of where MPI really shines, is now I don't have to worry about boundary conditions in general. I don't have to worry about doing any of the things that we did with, for example, with buffers in OpenCL, where we don't have any sort of Cartesian grid. We just have a pointer and dimensions, and we had to do all this math in terms of where am I in which row, my left neighbor is where, my right neighbor is where. MPI handles all of that, as well as all the boundary conditions for you, up to a certain limit. Yes? It's shift. So the shift 1, so the two things are direction and amount. So the first one means horizontal. 0 would mean vertical. And then I could put any value in there for 1. I could say 1, -1, 2 to hop twice. Diagonal one, I don't think you can. To do the diagonal one, you'd probably have to. Do you know? Have you done the shift with that? Diagonally, what you might have to do is do a horizontal shift and a vertical shift, and then transfer a message, right? Because you could say, okay, well, I'll do a vertical shift and a horizontal shift, and I'll take this one. I'll take this one and say, okay, what is your right neighbor? Pass that to your vertical neighbor. Because the ranks are still, it just gives you a rank back. It says you talk to this process number. So you can communicate those process numbers to other nodes, other processes. So you probably have this one say, you would have this one tell 0 what its right neighbor was to get a diagonal shift. There may be other ways. I don't know how common that is. That's certainly how I would do it if I'm limited to this. Okay. So for boundary condition, oh, sorry, good.
Yeah, so you get a three-dimensional grid, right?
Yep.
And so then you just take a different first argument to shift.
Yep. The other dimension, yeah.
And can you do periodic boundary?
I'll have to say that. I'm going to say that in a sec. All right, so but without periodic boundary conditions, so if you just got a grid, any send or receive that has an x, it has a special value. It's -2. -2 instead of -1, because -1 is very easy to produce accidentally as an off-by-1 error. -2 is a little bit more difficult. At least that's for the implementation I was using. It's -2. It means no process. If you try to send to no process, it just returns immediately. If you try to receive from no process, it also just returns immediately. You get no effect. So your data won't change. You'll get a none if you're doing the high-level Python. You'll just be that nothing was sent. If you had a buffer there, the buffer would just be left alone. And so that makes it very nice because then your code, right? I don't have to do any checks here. It's the same way when we load the Halo in OpenCL. Once the Halo is loaded, all our code is exactly the same. We know the data is valid for all our neighbors, regardless of where we are within the local work group. Same thing here. Once you set up the grid, it's not going to be necessarily valid, but you're not going to crash. You're not going to try to communicate with a non-existent process. And you don't have to figure out who your neighbors are or any sort of mapping. It also allows MPI to decide what the best mapping is. All right, so periodic boundaries. If we change the periodic argument, which has the same number of pieces as dimensions, for example, if we set it to this, then both of the dimensions become periodic. We could also interleave that. One could be periodic, one could be not. And periodic boundary conditions are basically wraparound. So if instead we pass in periodic true for the period, then the center one still gets the same neighbors, left and right. But then the 0 for its left source wraps around. And likewise for 3 for its destination for a right shift wraps back to 0. And then when we actually call a sender and receive, all the data passes this way and wraps around. That answer your question about periodicity? Yeah. So you can set that up arbitrarily. So the usual way you will use this is if you've got a very large domain you want to simulate on, 1,000 by 1,000 something. And you probably have a smaller number of processes than that. We're not in OpenCL where we've basically got a thread per pixel or thread per value. We've got some block we're going to operate on. You would do some local time step of your simulation in some subdomain, some subwindow of your process. You've got a very large image you want to process. You're going to process some subpiece of it. And then you need to communicate that the boundary has changed to your neighbors. And so you would take and pass a message from 0 to 1 that says, okay, I updated the boundary pixels in this region to these values. Likewise, 1 would send to 0, giving the same sort of information back, and then you would go on with your simulation. So if you're talking about weather simulation or image processing or anything like that, It's that sort of boundary domain, well, domain decomposition, where different processes are working on different pieces of the domain, and then boundary communication, sending just the updates that are needed between the individual processes. All right, is that clear? So why reorder? Why have Cartesian in MPI at all, right? All we really need is send and receive and some idea of our unique ID. Well, yes? Cartesian can do 2D, 3D. I think it can just do arbitrarily. I assume there's some limit, but I don't know what that size is. You can certainly go 3D. Why have Cartesian, I mean, we had a very nice, at the beginning we had send and receive, right? You send a message to someone, they receive it. And I said you could build everything on top of that. And in fact, that's the sort of stuff that we've been doing, for example, in OpenCL, where we just say, where am I? Where are my neighbors? Some barriers, maybe some communication using local memory. Why have this in MPI? It's because of where MPI is targeted, and it comes down also to this reorder, which says, can I change the ID or the position of the rank? Can I take the global rank or whatever and change it to something else and put things in different places how I want to? What's MPI targeted at? Supercomputers, which have a particular interconnect. Everything is not connected to everything. Some things can talk to other things more easily. And so by putting this in MPI, you can put, you know, if you've got some physical substrate this runs on, you can put process 0 here, or process 0, 0 in the communicator, and process 0, 1 there, and maybe 1, 0 that way. And so you can get a physical layout that matches you get a virtual layout that matches your physical layout. And then when you communicate with neighbors, you're basically, by setting up a Cartesian communicator, you're saying, I'm gonna talk to my neighbors mostly. And it maps it onto the physical hardware in a way that's efficient. You know, it might even stick, you know, some number of local processes, some block of your grid will go here, and then the next block will be in the next one. So back on slide 8, way back when I said the sender might hang until the receiver gets the message, right? And broke that immediately, that assumption, right? I send here, and I receive there. If that message were very large, unbufferable large, right, if I was sending gigabytes, this will hang, right? Everyone will try to send. And say, okay, I'm gonna start sending data. I get to some size, and then I can't just go on. I can't just throw a terabyte of data onto the network and say, okay, it's there, go get it, especially if everyone is doing the same. I have to have someone start to receive it. There's a limited sort of capacity that lives within the operating system, the pipe, and then the operating system on the other side. And when I overflow that, I have to wait till someone starts taking it back out before I can put more in the pipe. And so the way to avoid this, especially when you want everything to communicate to everything, where you want to do a data shift right and a data shift left, is to combine these two calls into a single call, which you do like this. So and again, on the high level, you can call send receive data, and you give a dest and a source. And MPI handles all of the buffering underneath. Basically guaranteeing that regardless of how large your data is here, it'll set up the incoming catch and start sending data out, and everyone will be working at the same time. And you don't have to worry about basically deadlock, right? It'll deadlock if you overflow the output buffer and everyone is waiting to get rid of their data before they start taking in new data. It's basically a deadlock situation where the deadlock, the shared resource is network capacity. So the send receive allows you to do that. You can do the same thing with the low level where you give an input and output. But in that case, you have to allocate a buffer yourself. So that's the better practice for any time you've got a block shift or everyone to everyone communication, is to do a simultaneous send and receive. And that's most of MPI for block computation. There are a couple more sort of high level, well, intermediate level things. So you have a couple of, sometimes you need to send data from one node to all the other nodes and the same value. In that case, MPI broadcast is your friend. Basically says, here's a node. It's again a single call. Everyone received from source 0 into this buffer, this value. If you want to split it up, you can do MPI scatter, where 0 also communicates with itself. It's important to note. Basically, you have however many values there are mapping to however many processes, and it splits it out and efficiently sends it to everyone. Which, especially if all of the data lives on 0 or is the only one that reads it, is very useful. Likewise, you can do this gather, which is the reverse of scatter. Pull everything from individual processes into one process. 0 has to allocate a buffer big enough to receive the message from everyone. And then all gather, if you want to do it, sort of a combination of gather and then broadcast. But more efficient to do it this way. It's single calls, and depending on what your substrate underneath is, what your network looks like, is going to be more efficient to do it that way. Likewise, there's a reduce with several operators, and an all reduce, which is just like reduce, but reducing to everyone. You have some set of operators here that you can choose. It's, again, somewhat limited by whatever has been implemented. I don't know what all the settings are there, but you can give it some set of arrays. You have to give this a type. You have to give this type information. It basically has to be a NumPy array, and you have to tell it what it is. And then it'll reduce across each element into a single node efficiently. That could be done hierarchically. Again, MPI doesn't specify how you implement this, and so that allows individual vendors and people who build supercomputers to implement it efficiently for whatever network topology they have. So you can reduce, you can do all reduce if everyone needs the answer. Again, it's the same as a reduce followed by a broadcast, but more efficient. And that's basically it. If there are questions about MPI, I'm happy to handle them. It gets very into the weeds after this quickly. I also wanted to spend some time if there are questions about final project requirements to discuss those today. There seemed to be a little bit of, as I posted on Piazza, I've heard, your TFs might be a little too nice to say, you need to do this, or this is these are the requirements that you need to land on. I want to make sure that it's clear what the actual requirements are. If you haven't, if there's something unclear on the list on the web page or something like that, I want to hear about it and explain it now. Anyway, questions about MPI? Totally clear? Great. Questions about final projects?
So can you clarify?
Can I clarify which?
Well, what are you expecting as like a parallelism? Like, for example, like my project uses Spark, but I'm not sure if like just using Spark is enough to show enough parallelism.
So in general, people, especially people using Spark, I've tried to be what is very easy to do is to solve a problem in Spark that could have been solved without Spark, and almost as easily, right? So if you're using Spark, we've tried to communicate to you what you need to do to make it interesting enough. In particular, one thing, look at scalability. It's a little bit tricky with Spark because it has a lot of overhead, but could you scale this up? How does it scale? Does it scale well from, for example, if you try it on a local machine, does it also work on AWS? What is your cost? What is the cost there? That's more going to be on a case by case. In general, for Spark, we're going to look for particularly other analyses done after using the Spark data, hopefully in parallel. also implemented in Spark. If, what? Spark is probably the most dangerous one in this respect, just because there are many problems you could solve in direct Python. You then implement them in Spark, it uses Spark, but now it's just slower, right? So in that case, we've tried to set out other goals there. If you're using OpenCL, you're going to show parallelism. It's especially, so there were some proposals with OpenCL that started out a little too easy in terms of, it's, you know, the Mandelbrot set is not a good OpenCL problem to try and demonstrate parallelism because it's embarrassingly parallel. You launch it on a bunch of pixels and it just goes, but there's no difficulty communication, there's nothing, you know, it's a warm-up problem for OpenCL. And so many of those we scaled up. So almost all the OpenCL projects now have some sort of component where it's, okay, you have to figure out how your data is moving around, you have to communicate between threads, you have to figure out how to do that efficiently. Similar for people who are working in Python. There are not actually that many people. I think you guys might be the only one doing a Python project, which is cool, because you're also doing MPI. But almost all the OpenCL, it's going to be, okay, you've got a hard communication problem on a very constrained architecture. So if you're having trouble finding parallelism, or if it's not obvious, you can't, it's like a thesis statement, right? When you do a thesis, like a PhD, master's thesis, your statement is, I am exploiting parallelism in this way for this project. If you can't complete that sentence, you should talk to your TFs and make sure that you can complete that sentence. So we're gonna look at how do you answer that question. I am exploiting parallelism by, I'm exploiting multiple machines to use large memory. I am exploiting parallelism by computing large image filters that vary over space, and I'm using OpenCL because I have a lot of computation that way. The other main concern why I posted that is I wanted to make sure people know that they should be producing code already. Right? It's still early, yes, it's still early, I guess, in some respect, but not very early. And so I was hearing concerns that they haven't started yet. You know, such and such group hasn't started yet. It doesn't have any code. That's worrisome, right? As I said, things are due on the 6th, it's the first, right? The screencast. There should be some results. There should be a serial implementation, if not now, earlier than now. Okay. Other questions about final projects? I just wanted to put some fear into you. I mean, not invalid fear.
What are like the little extraneous things do? Like the screencast and the website and
There's just really only 2 times. Everything is either due, the videos are due the 6th so that we can watch them on the 7th and 9th. So you may not have a complete implementation then, right? It's okay. Talk about your algorithm. Put something together in Keynote and talk over it. That's fine. Even if you're just discussing your algorithm, how you're leveraging it. It may not have all of your, and we're this much faster, right? You can say what your goal is if you haven't achieved it yet and whether you think you'll get that, what your maximum speed up could be. Some analysis and discussion of the algorithm, what's interesting about it. Some nice drawings so that your algorithm is transparent to people. And then the 10th is everything else. Website with write-up and the code. Here's our code, we committed it. How do you run it? There's got to be a README in there. We need to be able to run your code, or at least have a sense that we could run it. So this should include actual code, a README. On the website is even better. Here, documentation on the website with your write-up of the algorithm and the analysis and whatever else. Here's how we do it. The website can be, whatever. GitHub pages are nice, but whatever you want to do. So those are the only 2 due dates. Right. This should be about 2 minutes or so. Try to make it reasonably. We are going to watch them in class. Try to make it reasonably. I didn't say professional, but that's a good word. Make it. You're trying to explain your work to people, make them impressed by it. Talk about why it's interesting, how you're leveraging parallelism, what your hopes and dreams are for the project. All right. Other questions? All right. we don't meet again until Monday. Have a nice break. If you're traveling, stay safe. Don't expect a lot of tech support over that time. I mean, I'll be online sometimes, but not often. If it's urgent, good luck. Hopefully one of us will be on. All right, see you Monday.